superconducting qubit, the first thing we need to learn is the superconducting device, right? But what is superconductor? I think you all know superconductor. The first criteria I know you should know, at a certain temperature, right? Your resistivity, rho. When you usually for a metal or most material, when you reduce the temperature, resistivity keep going down, right? But for a certain temperature, it would just drop to 0. This is called the critical temperature, right? For example, for mercury, I think Hg, for example, Hg mercury, this is about 4.2 Kelvin. I hope I'm right. That is one thing. Now, that is the conductivity. But this is not the only criteria to make something superconductor, because this can be something called perfect conductor. It's just perfect, no resistivity. Okay? The second criteria is that very important. It has so-called Meissner effect. So what does it mean? So assume at the beginning I have a material, and then I have some magnetic field going through. And this is at temperature larger than the critical temperature, after which it will become perfect conductor or superconductor. If this is a perfect conductor, not superconductor, okay, perfect conductor, what will happen? Actually, if you look at Maxwell equation, of course, what I mean here is to cool it down, right? Cool down gradually. I just keep cooling it down, and then it suddenly becomes a perfect conductor because, yeah, perfect conductor, right? You will keep the magnetic field inside. Because if you try to solve Maxwell equation, it actually will say that you are a perfect conductor. You should not have any dB/dt. Otherwise, you are going to generate some issue. But if you are a superconductor, you are going to expel the magnetic field. It does not allow any magnetic field go into its body. And that's called Meissner effect, right? And that is the levitation principle of superconductor, right? So this is something good to understand. To be a superconductor, it needs to be 0 conductivity and also exhibit the Meissner effect, okay? And also I need to mention that superconducting state right, is only maintained if you know already temperature less than the critical temperature, but not just this. The current density passing through it less to the something called critical current density. If the current is too high, you will break the superconducting state. So this is a limitation. And also you understand later for Josephson junction why it has a critical current. Magnetic field needs to be less than a critical magnetic field, right? So you can understand that if you apply a very strong magnetic field, then you may lose your superconducting state, not just temperature, right? So this you need to keep in mind, the critical temperature, critical current density, and critical magnetic field, okay? Yeah.
Do you know if the critical magnetic field and current are dependent on temperature? Like if you you go lower temperature, can you put more current through it?
Right, usually it's like that if you have a larger, you're asking, okay, my answer want to say that if you have a larger magnetic field, then you will have a smaller critical current and also the temperature. Yeah, I think that's right. Yeah, that's a trade-off.
So because there's
Yeah, they will. Yeah. So then how do you explain the superconducting theorem, right? Material. Why there is superconductor? There's something called BCS theory. Badin, Cooper, and Schiffer. Badin is the guy who got 2 Nobel Prize, right? One is for inventing semiconductor device, transistor. Another is for this BCS theory. Okay? Because this is very weird. The so-called, to explain this superconductivity, it turned out that all the electrons are bound, there's a bound state for 2 electrons. All the electrons got paired together with opposite spin and opposite momentum. And this is something difficult to understand. How can you put 2 electrons together? Because they are both negative charge, right? And they will try to repel. And turn out the theory is that they are mediated by the photon. What does it mean? They will have some photon exchange with the lattice. Photon is the vibration of the lattice. And some hand waving, right? People like to, this is a very good analogy. It's like you have a mattress, right? And you have 2 balls on the mattress that you sleep. Mattress, right? You push it down, what happens? These 2 balls is going to go together. And that is an analogy. Your lattice is vibrating. It temporarily provides some positive charge to attract this electron. And then temporarily provides the positive charge to attract another electron. So it turned out it has lower energy if they can come together with the photon mediation. Right? So a very difficult math, I don't understand well, but that is how it works. Okay? But the main point here is this. What happens when you pair 2 electrons? Originally, I have 1 electron spin up. And then I have another electron spin down. When I pair them, it becomes a new particle, you can quasi-particle, no, I cannot say quasi-particle, a new particle, right, which is called Cooper pair. What is the spin of this particle? 1 spin up, 1 spin down. 1 spin up, 1 spin down. 0, right, they're opposite direction. Then it changed the property. This is no longer a fermion. So what is fermion? Fermion is a very important thing in quantum field theory, right? It has the spin, how to say, long integer spin. Long integral spin. For example, electron. It has a spin half. All this obeys Pauli exclusion principle, which you learn, right, in chemistry. What does it mean? What is Pauli's exclusion principle?
No 2 electrons can occupy the same energy with the same spin.
Exactly. No 2 electrons can occupy the same energy, same spin, right? Which means they cannot be at the same state. Once I occupy, no place for you. You need to go to another state, right? They exclude, right? So it follows, if you go through the thermodynamic statistics, it follows the so-called Fermi-Dirac statistics or distribution, right? What it means, the probability of it occupying at a certain energy equals to 1 over e to the power negative the energy minus a chemical potential divided by kT plus 1. I think no minus, I'm wrong. Just this, that's it, right? You learned this in semiconductor physics, right? E128, you have this distribution of the probability of how the electron will occupy, right? So if we remember that, if I put E here, and then this is the occupation function, and if this is the chemical potential, which is the Fermi level, you will get something like this, right? You will have a half probability to occupy mu when at the chemical potential or the Fermi level, you have half of the probability to occupy at that location. Is that okay? Pauli exclusion principle. It says people saying, I fill up this room, then you need to fill another room. I bought this house already, you bought another house. That is the fermion. But now, it becomes a Cooper pair. If spin equals 0, it becomes a boson with integral spin. That's just like the knights. The knights have spin equal to 1, right? So what happened? They obey Bose-Einstein statistics. It allows you to occupy at the same state. No matter how many, you are welcome, okay? So the distribution is 1 over e to the power e minus mu divided by kT minus 1. Let's take a look what it means. When t is very small, okay? And then E, how to say, equals to mu. Right? Maybe no need to start with E equals small. When E equal to mu, what is this function becomes? When E equal to mu, what is this? 1 becomes e to the power 0 minus 1, which is 0, right? Infinity. So you can just keep filling the same state. You're welcome. We can occupy the same state. And if E is larger than mu, but you have small t, when E is larger than mu, you have a small t. It means this is very large, right? Because positive number divided by a small number is large. And then exponential, this is super large, right? Then this is almost 0. So basically at low temperature, all the Cooper pair will just occupy the same state. Then what does it mean? It's just like laser. They have exactly the same state. And they behave like an army marching together. They becomes a macroscopic object. Think about the 10 micron of Josephson junction. And they all occupy the same state. The 1 to the power 23 electron pairs occupy the same state, right? So what I want to say is, maybe I will talk about this later, right? They occupy the same. So this is a macroscopic quantum object, superconductor. That is the cool thing about it. Okay? Yeah. That's all I want to have. Yeah.